So good afternoon. This will be Unit 3. This will be Lesson 6, Complex Zeros and the Fundamental Theorem of Algebra. This will be Chapter 5, Section 7. This will be the last section we do in Unit 3. Some of the key objectives we're going to talk about is conjugate pairs theorem. We talked about the conjugate earlier in Unit 2, I believe it was, working with quadratics. So we'll talk a little bit more about the conjugate pairs theorem today as well, a little bit different. We're going to find a polynomial function with specified zeros. So we're going to do that today. And we're going to find the complex zeros of a polynomial function. So remember, at this point, we've been really working with real numbers as our solutions. And remember, real zeros are going to appear on a graph as x-intercepts. Now, in working with polynomial functions, what we're going to pick up on is the degree indicates how many zeros are present. But sometimes the zeros are not real numbers, but they're complex numbers. So remember, complex numbers are in the form of a plus bi or a minus bi. So they have a real number component as well as an imaginary component. So remember, a represented a real number and bi represented an imaginary number. And remember, you cannot add those together. So where does this happen at? So remember, if we have this equation, x squared plus 4 equals 0, we're supposed to factor it. But what we've learned is this is actually not factorable. This is not a difference of squares. What we learned, though, is I actually can get the x squared by itself by moving the 4 to the other side. If we isolate the quadratic term, this makes this x squared equals -4. And when we get x by itself, we can take the square root of each side. So this is going to be x equals plus or minus the square root of -4. But remember, -4 gives us this imaginary unit. So this is going to be plus or minus 2i. So notice that we do have two solutions, but they're not real. They're actually imaginary, or we call these complex numbers. So this degree tells me how many zeros they're going to be, but sometimes they're not going to be real. So notice how we have, when they're imaginary, there's going to be 2 zeros. This is where this takes us into what's called the conjugate pair theorem. So in the conjugate pairs theorem, if one complex zero exists, then its conjugate must also exist. So if a polynomial has the complex zero -5 plus 2i, the remaining zero, the remaining complex zero is its conjugate. So it would be -5 minus 2i. That would be its conjugate. So remember, like have up here, if I have a plus bi, its conjugate would be a minus bi. If I give you a minus bi, the conjugate is always a plus bi. So notice it's going to be the same terms, but if one's positive, the conjugate's got to be negative. But if the term is negative, then the conjugate's got to be positive. So notice how the -5 and the 2i were present, but notice how the sign in the middle changed from a plus to a minus. So that's what we call the conjugate pairs theorem. So if one complex zero exists, then its conjugate must also exist. So that means there's going to be 2 zeros present. So if the degree is 3, and we have the zeros 3 and 4 minus I, notice that there should be 3 zeros altogether. So what does this actual direction say here? Let me jump back here. So we're going to use the given information about the polynomial function whose coefficients are real numbers to determine the remaining zeros. So all we're trying to do is find the missing zeros. So if I have 3 and 4 minus I, the remaining 0, well, since there's a 4 minus I here, its conjugate must also exist. So 4 plus I would also exist. So that would be the 3 zeros. 3, 4 minus I, and then 4 plus I would be the missing one. So if I have a degree 5 polynomial function, if the zeros given are 1i and -5i, we need to find the remaining zeros. So again, 1 is 1, but notice how if there's an I present, there also has to be a negative I present. And if there's a negative 5I present, there has to also be a positive 5I present. So notice how now we would have 5 different zeros: 1I, negative 5I, negative I, and 5I. So that's where that conjugate pairs theorem comes in. So if there's a positive I, there's got to be a negative I. If there's a negative 5I, then there has got to be a positive 5I. So if I have a degree 6 polynomial, and the zeros given are negative I, 5 plus 2I, and negative 6 minus I, what are the remaining zeros? Well, since each one of those is a complex number, all I have to do is use its conjugate. So if there's a negative I, then there's got to be a positive I. If there's a 5 plus 2I, then there's got to be a 5 minus 2I. So notice that the imaginary part's the only thing that changes. The real number part, the front number does not change. So if I have a negative 6 minus I, notice how I keep the negative 6, but the negative I turns into a positive I. So it's the imaginary part that changes sign, not the real number part. So that would be my 6 different zeros. So the negative I would give me the positive I, the 5 plus 2I gives me the 5 minus 2I, and the negative 6 minus I gives me the negative 6 plus I. So on this one, notice how we have a degree of 4. And the zeros are 4 plus I, and notice how 5 has a multiplicity of 2. So notice how here, since we have this 4 plus 3I, the remaining 0 would be 4 minus 3I. So notice that there's a 4 plus 3I, there's a 4 minus 3I, and since the 5 has a multiplicity of 2, that would be degree of 4 altogether. So there's the conjugate part, and then the 5 repeats twice. So we do have 4 zeros there. Just the 5 occurs twice. So next thing is we want to write the polynomial function for the above information and let a equal 1. So remember, to write a polynomial function, we're going to use this x minus r. Remember, that represents the factors. So the x minus r represents a factor. So to write a polynomial function, we got to change the zeros back into factors. So if I have this 4 plus 3i, then what we have now is x plus this, x minus, because that's our factor up there. We have x minus the 0, which is 4 plus 3i, times, we also have this remaining 0 here, which is the 4 minus 3i. So I can change that back to x minus this 4 minus 3i. I need an extra set of parentheses there. So I have that going on. And then my 5 has a multiplicity of 2, so it's going to be x minus 5 squared. So what we got to do is we got to multiply this all out. So let's start with this first part here. What I'm going to do is I'm going to bring this subtraction sign through and change this to x minus 4 plus, the signs of both of those have to change. Get rid of that. So I'm going to bring the subtraction sign through. So the 4 turns into negative 4, and the positive 3i turns into minus 3i. And then I have, again, this x, and I'm allowed to bring the minus sign through and make that a negative 4 plus 3i. And then x minus 5 squared, that's not too hard to do. Remember, when you have a binomial squared, the pattern says square the first term. That's just going to be x times x, which is x squared. To get the middle term, you multiply the x times the negative 5 and double it. That's going to give you a negative 10x. And then if you square the negative 5, that's going to be a positive 25. So that's going to be that. So what it boils down to is really trying to work out this front part. So I'm going to have to multiply this x through these three pieces. So it looks like we got a little work to do. Don't have any shortcuts here at this point. So x times x would be x squared. X times -4 would be -4x. X times 3i would be plus 3i. Now I want to bring the -4 through. So this -4 has got to go through all three pieces as well. So -4 times x is going to be -4x. -4 times a -4 is going to actually be a positive 16. I'm going to put that out here. And then -4 times 3i would be -12i. So that's going to be here, -12i. Let's keep my like terms together. And then my last thing I got to do is bring this -3i through. So -3i is going to go to the x, the -3i is going to go to the -4, and the -3i is going to go to the 3i. So -3i times x is going to be -3ix. I don't see that anywhere. So I have a -3ix, so that's going to come down over here. I missed that. I guess x times 3i at the very beginning would have been 3ix. So that's also 3ix. So let me back up here. I think I just missed that all the heck. So if you don't bring down the right terms, it kind of falls apart. So let's rewind here. Something looks suspicious there. All right. So I have to multiply this again, and let me see if I can do it correctly this time. So the x has to go through to start with. So this is going to be x times x. That's going to be x squared. Oops. Let me just go ahead and bring this through. X times -4, and then x times 3i. Let's see if I can do that correctly this time. Okay. So we have to do this multiplication here. X times x would be x squared. X times -4 is -4x. And x times 3i would be positive 3ix. So then I bring the -4 through. So -4 times -4 is going to be a positive 16. I'm sorry. -4 times x is going to be -4x. -4 times -4 is going to be a positive 16. He's not a like term. And then -4 times 3i would be -12i. So -4 times x is -4x. -4 times -4 is a positive 16. And -4 times 3i is -12i. That looks good. I now need to bring the -3i through. So -3i times x is going to be -3ix. -3 times a -4 is going to be a positive 12i. And -3 times positive -3i times a positive 3i is going to be a -9i squared. So we have all that going on. So the x squared is going to come down. The -4x's, that's going to be -8x, comes down. The 3ix and the -3x zero out. The 16 comes down. And the -12i and the 12i cancel out. And I have this I squared to -1, so that turns into a +9. So what I have now is this x squared minus 8x plus 25 comes down. So I want to now multiply the x squared minus 8x plus 25. I still got to multiply that to x squared minus 10x plus 25. So if I do that, I have then x squared times x squared is x to the 4th. X squared times -10 would be -10x to the 3rd. X squared times 25 would be a positive 25. x squared. Negative 8x times x squared would be negative 8x cubed. Negative 8x times negative 10x would be a positive 80x squared. Negative 8x times 25, that would be a negative 200x. Numbers are getting a little bigger too. Almost reached for a calculator there. So 2 times x squared would be 2x squared. 2 times negative 10x would be negative 20x. 2 times 25 would be 50. So our function is going to be then f of x equals x to the fourth minus 18x cubed plus, looks like what, 105, 107x squared minus 220x plus 50. That would be the polynomial function they're looking for. And again, they're saying a is equal to 1, so we don't have to mess with the a in this problem. It just stays there. So find the remaining zeros of a polynomial. So again, strategy for this as we move forward is going to be identify the factors. We're going to multiply them together if there's more than one. We're going to divide the polynomial to get the remaining quotient. And we want to factor the remaining quotient if necessary. And we want to set the factors equal to 0 to find the remaining zeros. If the remaining quotient is quadratic, but will not factor, we have to use what's called the quadratic formula. Okay, that was a mouthful. So we're going to be given a polynomial function and we're going to be asked to find the zeros. So let's see what our strategy is going to be. So we have this function here, and we want to find the remaining zeros. So right now I know that 3i is present. So I know one of the remaining zeros has to also be negative 3i. Okay, so we've got 2 of the zeros. Okay, now what I want to do is I want to identify the factors to start with, and I want to multiply them together if there's more than one. So what I found is 3i is a 0 and negative 3i is a 0. So what I have are 2 factors. So x minus 3i is a factor, and x minus a negative 3i is a factor. So in other words, we have x minus 3i times x plus 3i. So we found our 2 factors, and we want to multiply those together. So x times x would be x squared. X times 3i would be a positive 3ix. Negative 3i times x is going to be a negative 3ix. And negative 3i and a positive 3i is going to be a negative 9i squared. So what we end up with then is x squared, the 3ix and the negative 3ix cancel out. And the I squared makes a negative 1. So that negative 9 turns into a positive 9. So it's going to be x squared plus 9. So we have that going on. So we multiply those 2 together. So what's our next step after that? So we want to divide the polynomial to get the remaining quotient. So I want to divide the x squared plus 9 into the polynomial. And notice the degrees count down 3, 2, 1, 0. So x cubed minus 5x squared plus 9x minus 45 would be the polynomial. So again, x squared goes into x cubed. In other words, x squared times what gives me x cubed? Looks like I'm just missing an x. So x cubed times x gives me x cubed. So notice how all I got to do is focus on the front end. The rest of it will take care of itself. So x times x squared would be x cubed. X times 9 would be a positive 9x. Now remember, in long division, we're supposed to be subtracting, but the strategy we use here is we just change the signs and add. So that becomes a negative, and that becomes a negative. So the x cubes will cancel out. I have a negative 14 Was that a negative 9x? That doesn't even go there, does it? Sorry about that. He needs to slide down one. Make sure you line up your like terms correctly. So that x times 9 would be a positive 9x. So it should be going down here. So again, when I changed my signs, this became a negative and that became a negative. So this negative 5x squared comes down. The 9x, the negative 9x cancel out, and we have this minus this 45. So now we ask ourselves, x squared times what gives me negative 5x squared? Looks like all I need is a negative 5, so I'll put a negative 5 here. So negative 5 times x squared is negative 5x squared. Negative 5 times 9 is negative 45. So my like terms are lined up there this time. So remember, we are subtracting, so these signs have to change. That turns into positive, that turns into positive. So that means my remainder is a 0. If my remainder is 0, then x minus 5 is a factor. So x minus 5 is my remaining factor. Now, what do we have here? So divide the polynomial to get the remaining quotient. Factor the remaining quotient if necessary. Set the factors equal to 0 to find the remaining 0. Well, all I'm left with is x minus 5. So all I got to do is set that factor equal to 0 and solve for x. So x is going to equal then this 5. So the remaining zeros, let's see, what was our directions again? Find the remaining zeros. So since 3i was present, one of the remaining zeros was negative 3i. And then I use that information to find the other 0, which is a 5. So I found 3 zeros, and notice that the degree was a 3. Since the degree is 3, there has to be 3 zeros. 2 of them are complex numbers, and one of them is a real number. So we're there. So let's look at this next one. F of x equals 4x to the 4th plus 7x cubed plus 62x squared plus 112x minus 32. One of the zeros is negative 4i. So that means a remaining 0 would also be a positive 4i. So what our next step is to multiply those two zeros together. In other words, we need to change them as factors. So the x minus 4i turns into x minus the negative 4i. And the 4i turns into x minus 4i. So we're going to multiply those together. But also how two negatives make a positive. So that turns into x plus 4i times x minus 4i. What you should recognize, these are conjugates. So as a shortcut, all you really have to do is multiply the first terms together and multiply the last terms together. So I'm going to do that a little quicker this time. So x times x is going to be x squared. 4i times negative 4i is going to be negative 16i squared. So that's going to be x squared plus 16. Okay, so if we go back up here, notice how the middle terms kind of canceled out. So this time I'm going to take a shortcut and not worry about the middle terms because they're going to cancel out. So this is a difference of squares concept. The middle terms are going to cancel out. So all I got to do is multiply the first terms and the last terms together, and we have it. So I'm going to use this expression x squared plus 16, and I'm going to divide that into the polynomial. So I have 4x to the 4th plus 7x cubed plus 62x squared plus 112x minus 32. So again, all we got to do is focus on this front part. X squared times what gives me this 4x to the 4th. So that's going to give me, I need a 4 and an x squared. So 4x squared times x squared would be 4x to the 4th. That's what we need. And 4x squared times 16 is 64x squared. That's going to go down here. Now remember, we're supposed to be subtracting. So what I do is change the signs and add. So the 4x squared, I'm sorry, the 4x to the fourth and the negative 4x to the fourth are going to zero out. So the 7x cubed would come down. And this is going to give me a negative 2x squared plus 112x minus this 32. I may as well go ahead and bring it all down before I lose it. So now we focus on the x squared and figure out what can we multiply it by to get this 7x to the third. Looks like I need a 7 and an x, so I'm going to put a plus 7x here. In doing so, we now multiply the 7x times the x squared, and that's going to give me 7x cubed. 7x times 16. Well, I need to multiply 16 times 7. Well, I'm going to do that over here. Looks like 112. So it's going to be a plus 112x. So that's actually going to go over here. So let me get rid of that plus sign there. Make sure our like terms are lined up. So we now need to finish this off. So we subtract, in other words, we change the signs and add. So this negative 2x squared comes down, and this minus 32 comes down. And then we look at this again, ask ourselves, well, how many x squareds will go into negative 2x squared? That looks like that's going to be a negative 2. So negative 2 times x squared is negative 2x squared. Negative 2 times 16 is negative 32. So again, we want to subtract. So these signs change to positives. So that cancels out, and that cancels out. So our remainder is 0. So we're left with 4x squared plus 7x minus 2. So that's what we're left with. 4x squared plus 7x minus 2. So to factor this, I'm going to use 4 squared. See if it's factorable. So the quadratic term goes to the top left. What goes in the bottom right is the negative 2. Now the catch is when we use big T, we got to multiply the leading coefficient to the constant. So 4 times negative 2 is going to be negative 8. And we have to add up to this coefficient, which is a 7. So what are the factors of a negative 8 that give me a 7? That looks like an 8 and a negative 1. 8 times negative 1 is negative 8, and 8 plus negative 1 is negative 7. So what we do is we break apart the middle term into 8x and negative 1x. Now the strategy here is to pull out the GCF. So the GCF here is going to be a 4 and an x. So a 4x comes out. And what's left then is 4x times what gives me 4x squared. Notice how that's that division stuff again. 4x times x is 4x squared. 4x times what gives me 8x would be, I would need a 2 there. And what times x gives me negative 1x, I need a negative 1. And does negative 1 times 2 give me negative 2? It does. So I can use that as a strategy. So again, we're going to set this equal to 0 to find our remaining zeros. And that's going to factor into 4x minus 1 times x plus 2. So now we have to set each one of those factors equal to 0. 4x minus 1 is equal to 0. X plus 2 is equal to 0. 4x is going to equal 1. X is going to equal then 1/4. Here, x would equal a negative 2. So the remaining zeros, well, we had 4i, we found at the beginning, and then we have this 1/4, and we also have this 2. So we have 3 remaining, plus the original, which is the negative 4i. Notice how the degree was a 4. So we were looking for 4 zeros. They gave us 1, and we found 3 of them. So that's solving that problem for the remaining zeros. So finding the complex zeros of a polynomial function. If the degree is odd, there must exist at least one real zero. we want to identify the possible rational roots. So that's that rational roots theorem that we did earlier. Use either synthetic division or f of r to identify the zero. We want to use synthetic division to find the remaining quotients. Repeat this step until the remaining polynomial is a degree 2. Factor the remaining quotient or use the quadratic formula where necessary to find the remaining zeros. So notice how this polynomial is a degree 3. That means it has to have at least one real zero. So what we can do to start with is identify the rational roots. So remember, that's where we have to identify this p over q. Well, p is the factors of this negative 26. So what we have there is for 26, if we use big T, we have 1 and 26, 2 and 13, and then it would be back to 13 and 2. So that would be our 4 different factors. So plus or minus 1, plus or minus 2, plus or minus 13, plus or minus 26. Those are our possible P's. Our possible Q's are the factors of the front coefficient, the leading coefficient, which is the 1. So that's only plus or minus 1. So P over Q. So our possible rational roots are 1 over 1 would be just 1. So plus or minus 1. 2 over 1 would be plus or minus 2. 13 over 1 would be plus or minus 13. 26 over 1, well, that would just be plus or minus 26. So we have 8 different choices for our zeros, our roots. So what we want to do, I'm going to use this f of r. Remember, if f of r is equal to 0, then that is a root or a 0. So using my calculator, I'm going to type in this function. So I'm going to have to slide this over so I can see it. It's too big. So I'm going to have then x cubed in my calculator minus 8x squared plus 25x minus 26. Okay. Under table set, I'm going to change it from auto to ask. Well, it already is. All right. So I don't have to do that. So if I now go back to my table, so if I clear this off, I think I have to hit the delete button. Try that out again. Hit the delete button. There you go. That goes away. So let's try 1 to start with and see what we get. So if I put 1 in, I'm looking for 0. I got a negative 8. So let's try a negative 1. And I got negative 60. Let's try a 2. 2 gave me 0. So there's my winner. So I found a root. So 2 is a root or a 0. Okay. So 2 is a 0. So I found one. So if 2 is a 0, that means x minus 2 is a factor as well. So what I can do is, since I found a 0, what I can do is use synthetic division to find the remaining quotients. So instead of dividing by x minus 2, I'm going to use 2 as my number out here. And so I now just need the coefficients. So 1, a negative 8, a 25, and a negative 26. So if I do that long division, I'm going to leave a little space here to do some math. So the 1 comes down, and then we just multiply the 2 times the 1, which is 2. A negative 6 comes down because we're adding those together. 2 times negative 6 is negative 12. Negative 12. 25 plus negative 12 would be a positive 13. And 2 times 13 is 26. And negative 26 plus 26 is a 0. So remember, this is our remaining polynomial, but remember the degrees have to go 1 less than what we started with. Since the degree up here was cubed, this becomes my x squared term. So instead of saying 1x squared, we're just going to say x squared minus 6x plus this 13 is equal to 0. So we're going to set that equal to 0 to find our remaining zeros. So what we look at then is, what are the factors of 13? Well, the factors of 13, there's only 1 and 13. There's no way that's going to give me a -6. So this tells me that it's not factorable. So the only way to solve this quadratic equation is to actually use the quadratic formula. So we're going to use the formula x equals -b plus or minus the square root of b squared minus 4ac all over 2a. So remember, a is the coefficient of the x squared, so a is going to equal 1. B is the coefficient of the linear term, that's a -6. And the c is the constant, which is this 13. So when I'm solving for x, I have to take the opposite of b, that's going to be a 6, plus or minus the square root of. So I have to do a -6 squared, which is actually 36. So I'm going to go ahead and do that math. Minus 4 times a, which is 1, times c, which is 13, all over 2 times 1, which is 2. So using my calculator, I'm going to work that out with the calculator. So I'm going to quit that. So I'm going to do what's inside the square root symbol in the calculator. 36 minus 4 times 1 times 13. Now, if you keep the -6 squared, remember you would have to use parentheses there. So I get a -16 for that. So what I have now is 6 plus or minus the square root of -16 all over 2. I don't need that a there. 2 times a was actually just 2 times 1. That was just 2. So remember, the square root of a negative number is the I. So this becomes 6 plus or minus 4i. Because the square root of 16 is 4, and that negative comes out as an I. So now we're allowed to separate this as 2 separate fractions. So that's 6 over 2 plus or minus 4i over 2. So 6 over 2 turns into a 3. 4i over 2 turns into a plus or minus 2i, since I can divide 2 into 4 and get 2. So I have 3 plus or minus 2i. So did we find all the zeros? So remember, we found 2 as a 0 up here, and we found 2 complex zeros. So that's a total of 3 zeros. Since the degree is 3, we have found all the zeros. So the zeros for this problem, so the complex zeros, if you will, is going to be a 2, a 3, plus or minus 2i. That would be the 3 different complex zeros. So let's look at one more type of example. If the polynomial function is even and does not have any real zeros, a quadratic form can be used to find the complex zeros. So let's look at the function f of x equals x to the 4th plus 13x plus 16. Notice how this function is even. It's not a bad idea to graph this thing just to see if it has any x-intercepts, because if it doesn't have any intercepts, then there is no need to use the rational root theorem, because it only finds real zeros. So if I look at this problem here from a graphing perspective, I'm going to probably switch this over here. It's too much for me to remember. I'm sorry. So we're going to type in this x to the 4th plus 13x plus 36. If I hit the graph button, don't see anything. Let's change my window. Notice how that's like all that. So let's go to zoom, and number 6 puts it to a normal window. I still don't see anything. So notice how the y-intercept would actually be 36. So I know I need to go up past 36 anyway. So let's change the window where the y max is, say, maybe 100 or something. If I do that, let's change our scale to go by 10, so there's not a ton of tick marks. If I hit the graph button again, notice how we get this function here. It kind of takes on this look. Okay. So notice how this graph is above the x-axis. So this should actually be 13x squared. I'm sorry. I wrote the problem down wrong. Okay. So this is actually 13x squared. This function is actually an even function. So let me try that again. Made up the wrong problem here. Let's see here. I need a 13x squared. That's the one that you're going to have in your homework. So let's make it look like your homework. Plus this 36. Now if I hit graph again, yeah, that's more like it. Because even functions are supposed to be symmetric with respect to the y-axis. So notice how the degrees are 4, 2, and 0. That makes it an even function. That's what we were looking for, actually. Sorry about that. So what we pick up on is there's no need to do the rational root theorem because there's not any rational roots. All 4 zeros are complex. So to do this example, we use a little bit of trickery. Instead of since we have this x to the fourth here and this x squared here, we're allowed to let u equal x squared. So what happens is x to the fourth is really x squared. Let me make this bigger. X to the fourth is really x squared squared. If you square x squared, that gives you x to the fourth, plus this 13x squared, plus this 36. So this still means the same problem. And what we're going to do, though, is where there's an x squared, we're going to replace it with a u. So that's now going to become u squared plus 13u plus 36. By doing so, this equation becomes quadratic. Okay. Now, again, the factors of 36, we should know that this isn't going to factor because there weren't any real zeros. But notice how, again, if I look at the factors of 36 here, let's see what happens. Maybe this thing does factor. So we have 1 and 36, 2 and 18, 3 and 12, 4 and 9, 5 doesn't work, 6 and 6. Errors repeat. 4 and 9 actually do work here for us. That does give me a 13. So this actually turns into a factorization. So got ahead of myself there. That's kind of nice. So this is going to turn into u plus 4 times u plus 9 equal to 0. So what we're going to do is we're going to have u equals -4 and u equals -9. But remember, we're solving for x. To solve for x, I can now jump back in and replace u with x squared. So what I actually have now is x squared equals -4 and x squared equals this -9. Now remember, to take the square root of each side, we'll solve for x. So x is going to equal then the plus or minus the square root of a -4. Because remember, when you do it this way, you have to put that plus or minus there. So it's going to be a plus or minus the square root of -4. And this is also going to be x equals, remember to put the plus or minus the square root of -9. Now remember, the square root of a negative number is actually I. So this becomes x equals plus or minus 2i. And over here, this becomes plus or minus 3i. So those are our 4 answers. And notice that every one of these would be a complex number. So those are 4 complex zeros. So that's how we can solve a complex problem where I can't find any real zeros. Is sometimes we're allowed to use a little trickery. Since this was an even function, we're allowed to use this u equals x squared as a strategy. Okay, so that completes our lesson on 5.7. So I'll let you go and y'all have a good day.